Okay, and we should be live currently. So, hello everybody, and welcome to Discussions in Orbit, REXUS BEXUS Edition, our new series of live interviews organized by Team DROPSTAR. If you're familiar with DROPSTAR, you know that our team participates in the REXUS BEXUS Programme, a German-Swedish student program where teams of all over Europe are selected to design, build, and execute an experiment in one of the two available platforms: BEXUS, a stratospheric balloon, or REXUS, a single-stage rocket. In Discussions in Orbit, REXUS BEXUS Edition, we interview fellow REXUS BEXUS teams in order for them to introduce their experiment to the public and share their experience in the program. So, the first team here is Team Trace.
Great, so hello from me as well. Team Trace is a student team from Germany, which will be participating in the REXUS BEXUS program. In particular, their experiment will be executed in the REXUS Rocket, where our experiment DROPSTAR will also be executed in March 2024. The experiment aims to test and validate transpiration cooling heat shields in a re-entry vehicle in a free flight experiment. This cooling method is achieved by blowing a cooling gas through a porous material that is surrounding the structure to reduce its thermal loads. A big goal of the team is to make that system reusable, which, as they say, will be achieved by just refilling the gas in the cooling tank. But I think we should hear more about the team themselves, as they definitely know their experiment better. So, hello, Team Trace, and thank you for being with us today in the premiere of the series. We would like for you to introduce yourselves to the public.
I'll go first. My name is Timo. I am a mechanical engineering student with a focus on aerospace sciences. And in Trace, I work on electronics and software.
Then I will go next. My name is Sebastian. I joined Space Team Aachen in 2020 and then the project Trace in 2021 as a simulation engineer. So I'm working on the trajectory calculation. And I'm currently in my master studies, almost finished. My master thesis deadline is 2 weeks away, so almost done there. And I'm hoping to finish my studies with a very cool project, which is Trace.
Yeah, hi from my side. My name is Nicholas. I study mechanical engineering too, with a focus on aerospace engineering, and I'm the project leader of this whole Trace thing. And yeah.
My name is Rishabh. I'm also studying mechanical engineering with focus on CFD simulation. I'm also working on my master's in direction of transpiration cooling, where I will simulate a real-world re-entry scenario for with higher Mach numbers, and also simulate the cooling with blowing a cooling gas that happens on a boundary layer. I joined CIST as a mechanical engineer last year. And then I moved to simulations, where I'm now working on CFD analysis of cooling. Yeah, that's it.
That's great. So I think we should begin the interview by the most basic questions of all. So we would like for you to describe to us the concept of your experiment. What is the Trace experiment?
Yeah, I'll start with that. So Trace itself stands for Transpiration Cooling Experiment. And basically, as you mentioned earlier, we want to test a new type of heat shield. Well, it's not that new, but at least the real life tests are pretty new. And that heat shield is based on transpiration cooling. So it's an active cooling method. And yeah, so the whole principle how we want to test that heat shield is, as you can see right now on the video, is to be in the nose cone of the rocket, and then the nose cone is ejected, and our capsule itself is ejected, and then this whole capsule that you saw on the second screen is going to drop down to Earth and reach speeds of Mach 3.2. and temperatures of up to 500 Kelvin. And we then will activate this transpiration cooling heat shield and, well, cool our capsule, at least from one side down. and the other side is going to be used as a reference side to compare basically the two sides and how effective the cooling actually was. And therefore we are split into teams to work on all the mechanical parts so that everything actually holds together. And then we also have the electrical part for all the sensors, but also all the software that needs to activate all parts since it's an active method. And lastly, we also have the simulation because we have to have a pretty accurate trajectory to know where exactly to activate our cooling. And that's basically the whole concept of trace.
Right. So in your experiment, as we currently heard, you are running both the experiment and the control, so you have directly comparable results, which is really great, honestly. And what are the goals of your experiment? What do you expect to achieve with this device that you're putting on REXUS?
Yeah, so we have defined for ourselves three main goals. And the first one, as Nicolas already said in the beginning, is to demonstrate a transpiration cooling system in flight. So far as we know, that's only the third time that's being done. All other times have only been in the wind tunnel. But of course, a real flight test is always better. So we seek to see a transpiration cooling system perform in actual flight conditions and investigate the data afterwards and gain more insight into this new cooling technique. Our second goal is related to computational fluid dynamic analysis, or short CFD. So designing a transpiration cooling experiment is pretty difficult, and so is trying to simulate it. But if we successfully perform this experiment, we will have a lot of data which we can validate CFD simulations and learn how to improve CFD simulations for future experiments or even spacecraft. And then our third goal is more related to the general mission of Space Team Aachen. So Space Team Aachen has the motto of providing practical experience to students. And TRACE is also part of that, in that it's a really challenging project with which we can learn a lot about how to apply the knowledge we learned during the studies to a real-world problem.
Amazing. So, transpiration cooling. What is the science behind this phenomenon? Can you describe it to the public?
I'll take that. So, cooling of re-entry vehicles is something we have been doing for a long time, from one-time use space probes as well as reusable crewed vehicles. Earlier, we used ablative shields, which technically burn themselves in order to protect the vehicle and thus cannot be reused. So you have to put a new shield every time if you want to use the aircraft. Then for the space shuttle program, NASA developed a new technology that is a thermal soak heat shield, which is just a big array of tiles on the surface of the space shuttle, depending on different temperatures, different materials were used to make them. These tiles are replaceable, so they don't get destroyed in re-entry, and they can be replaced if damaged. So you don't need to change the whole heat shield. There's just some tiles where you have high damage, and they technically soak the heat and can re-radiate the heat, thus cooling themselves. The major problem with both these methods is, yes, of course, the reusability, and then the second part is high maintenance costs, because we all know about the Columbia disaster, which happened because a few of these tiles got dislocated and detached from the surface of the aircraft. Transpiration cooling in this matter does not depend on some material covering the surface of the aircraft, rather than we try to cover, in simple words, to make a layer of a fluid around the spacecraft, which technically prevents convection heating. So we eject coolant gas into in the supersonic or hypersonic boundary layer, where as the aircraft is flowing into the Earth's atmosphere, the coolant ejection will form a film around the spacecraft, or you can also have thermal mixing and the near trailing edge of the aircraft, which essentially prevents the convective heat transfer between the air and the surface of the aircraft, and thus protects your re-entry vehicle from the excessive heat load. It also can prevent radiative heat transfer, which is one of the few which is one of the few modes of heat transfer which happen at low atmosphere, low heights in the atmosphere, and where convective heat transfer is not efficient enough for cooling.
Well, I mean, it sounds quite complex, to be honest. I think it's a subject that deserves a lot of study, experiments, because it seems like it has a large amount of theory behind it. And you hope to study this during the 10 minutes flight of a REXUS rocket. Can you describe your timeline? Like, in those 10 minutes, what will be happening inside your experiment?
Yes, so I will be starting from the very start, which is actually before liftoff. So we'll have the end of radio silence 15 minutes before liftoff, and then some system checks 10 minutes before liftoff. And at that point, we will finally be ready to perform the actual liftoff, which I think is the moment we are all most looking forward to watch the rocket go to the sky. And about 1 minute into the flight, the nose cone will be ejected by the REXUS rocket, and shortly after, we ourselves, meaning the TRACE experiment, will also be ejected. And at that point, we are on cruise flight, and we're going to reach apogee, so the highest point of our trajectory. And from that point, we're going to go down really fast. And we're going to reach a point where the heat flux, so the thermal load that is being imposed on the capsule, is going to reach its maximum. And we're going to try to time our experiment in such a way that the cooling fluid is expelled at this moment so that we can test our system in the most difficult conditions possible. And after this experiment is finished, we'll keep flying for a bit at, continuing at really high speed. And then the boat tail will be separated. If you look at the trace capsule that is standing on the table in the stream from Richard and Nicholas, that's going to be the part at the bottom. And it's going to eject, and at that point, we're going to deploy our supersonic parachute, which will slow us down from supersonic speed to a bit slower, below supersonic speed. And once we've reached a certain terminal velocity there, then we'll deploy another parachute to really slow us down. So when we hit the surface, we don't just explode or are completely disintegrated. And at that point, Trace will be laying on the floor. And we will start to try and recover the capsule. For that, we have a beacon in there. And we'll have to be a bit fast because the power will run out after 5 hours. So if we don't find the trace capsule within 5 hours, we'll probably not find it again, which would be a pity. And at that point, we'll take the capsule home and evaluate the data and work with that.
So it's a very tight timeline. I think we know it ourselves from our experiment DROPSTAR that the REXUS timelines are very, very tight. You have to be focused and everything has to work properly. And we also know that each REXUS BEXUS experiment is innovative and unique. So what are Trace's unique technical characteristics that give it its innovative character?
Yeah, so as I said, as I explained, transpiration cooling is not simple, it's a bit complex. And that's why it's not been tested many times. So this is one of the kind of experiment which we are doing. It's only a third time we are testing such kind of heat shield experimental. Theoretically, we have a lot of research done analytically or numerically using CFD or turbo solvers, but experimenting as an experiment, this will be a third of its kind. We have a very unique, innovative pressure tank, which is like the heart of the system where we will store the coolant, which is going to be blown into the boundary layer for coolant. We have 3D printed the whole thing with a high density titanium alloy. And then, of course, when we are recovering the vehicle, we need to slow it down enough so that it does not hit head down on the ground and destroys itself. So that supersonic parachute, which is first time developed at the Space Team Aachen, which can not only work at the supersonic, it can work at different sonic numbers of Mach 2 and beyond with high safety factor. So overall, this is a very unique experiment from people at Space Team Aachen as well as from the technology which goes behind it.
Wow. I mean, the more we talk about your experiment, I mean, I selectively did not read too much into your experiment because if you already know the answers, you don't you don't engage in such a way. But the more things you say, the more I'm like, wow, you had to face so many problems, and you probably had many difficulties up until now. So can you describe some of the main difficulties that you had to face and how you approached them?
Yeah, so the whole difficulty started with the bachelor thesis to answer if this is feasible in the first place. And so the result there basically is we need to be very fast in a dense atmosphere to reach a high enough heat load to actually test this whole heat shield. And so, yeah, so we had to optimize the whole capsule aerodynamically so we don't have too much drag. And that comes with challenges in itself. For example, we also had to not use fins or something like that would create drag. We had to stabilize our whole capsule passive. And that was a challenge. And then obviously with the high speed and the high density of the atmosphere, this atmosphere only gets dense at lower heights, and we still are very fast. And so that means that, as Richard mentioned earlier, we're going to have to use a parachute that opens at those fast speeds, and that not in like a very high altitude where the atmosphere is not that dense, but actually in a higher density atmosphere. And so the loads on that parachute are very much high due to the supersonic speed, but also due to the high density of the atmosphere. And then lastly, one of the biggest challenges we actually faced is the miniaturization of the experiment, since we have quite some systems in there. Since we're a free-flying unit, we need to recover ourselves. So the parachutes already take half the space, well, 1/3 to half the space. And then in the other half, we have to pack our whole cooling system, all the electronics, and a separation system to eject the parachutes. And then also something to passively aerodynamically stabilize the whole capsule. So it's a whole bunch of systems. And so the solution was there, as Richard mentioned earlier, for example, the pressure tank. We couldn't find space to put a pressure tank that was in the shape of a sphere, since that would take too much space, and we don't have space for the other cooling system, the tubes and stuff like that. And then obviously also not for the electronics. So what we did is actually make a tank that doesn't look like a tank, it more looks like a potato. So we call it our pressure potato. And it basically is not very good in pressure distribution, but it saves a whole lot of space. And so that was one of the solutions. But that was definitely the hardest challenge to miniaturize all this experiment. Yeah.
Sounds like a lot of difficulties, but I think a great team can give solutions to these problems. So I think now is the time for you to tell us more about your team, because you do have a very interesting experiment, so you must have a very well coordinated team.
I would hope so. Yeah, so I mean, I'll start a bit at the back. We mentioned earlier quite some time the Space Team Aachen. So we are actually part of a bigger organization, which also helps us a lot to figure all this out, because for most of us, and I guess for you guys too, it's the first thing we ever do in our life that comes that close to all this engineering and space technology. So we have the Space Team Aachen. It's our parent organization, and we come from the RWTH Aachen and the FH Aachen University from Germany. We have 150 plus members now, so we're quite big. And then our goal is, as Sebastian mentioned earlier, we want to gain hands-on experience as a whole Space Team Aachen, and therefore we participate in international competitions. For example, in a month or about 2 months, our rocket Aquila will fly at the SAC in the USA. And so our general activities for the Space Team Aachen is just development, manufacturing, testing, and then also flying all the stuff we create. And just to a quick rough view of the projects, we have rocket projects, as I mentioned, the Aquila. It's going to be our first supersonic rocket. And then we have Star, where we create our own hybrid rocket engine. And then we also have the Alea rocket, where we investigate thrust vector control to use it for us. And then we also have the scientific projects. That's what TRACE is part of. So TRACE, the transpiration cooling experiment. And we also have AACHEN, a nanosatellite that is going to go into orbit and take a picture of the Earth. And then we have a very new project, just a couple months old, the space rover. That's the Space Team Aachen. And then our team ourselves, so the TRACE team, we're organized in many teams. We have me, the project manager, but also a system engineer, a test engineer, very important. Well, all are very important, obviously. But we recently only got a test engineer since we struggled a bit to find the time to create all the tests we need. And we have a test engineer, but also a head of electronics, because the system engineer and I, and the test engineer too, actually, we're all mechanical engineers. And so for all the electrical things, we're not that smart. So we let a proper lead for the electronics. And then we're divided in many groups. The mechanical work group to do all the mechanical stuff and also the cooling. And then we have the simulation work group where Sebastian is part of. That's the trajectory simulation, the simulation of the cooling itself. And then lastly, we also have the electronics work group where Timo is, and that's software, electronics, hardware, all of that. And then I forgot, but also very important, advisors. As I mentioned earlier, most of us are the first time we do such a thing, and we have help from Space Team Aachen itself, and more experienced people from the Space Team Aachen. And that's our team and our team structure.
You have quite an ambitious experiment that you're running with the team. And I think people would like to know what you expect that the contribution of your experiment would be. The first thing that one would probably think about is, do you believe that your experiment and research could contribute to the development of such systems for standard flight equipment? So, for example, an ESA or NASA or whatever space agency rocket could probably use a technology like the one you're showcasing right now in the future?
Yes, we sure hope so that one day transpirational cooling will be a commonplace part of spaceflight. Of course, we can't say yet how big our contribution is going to be, but any type of data collection in this field is always going to be helpful. So I think we're doing at least our small part in this whole endeavor, and we hope to help this whole effort. And the other side effect we have, of course, we have now like 20 people who have already worked in transpirational cooling. So our contribution is not only going to come through creating this experiment, but also by educating our team and becoming better aerospace engineers. And the contribution is not only limited to the transpirational cooling. As said before, we also have the additively manufactured pressure tank, or 3D printed, as it's known in the general public. So we also gain a lot of experience there, and also came up with some pretty innovative concepts, which might be helpful for other projects in the future.
Great. Very, very good. So to wrap this first interview in Discussions in Orbit, REXUS BEXUS Edition, we would like for each of you to tell us about the REXUS BEXUS program. What are the lessons that you have learned so far, and what advice would you give to future REXUS BEXUS participants?
I think Timo has an answer to that.
I was just about to unmute, sorry. Yeah, so let's start with some lessons we've learned along the way. I think if you are starting, and maybe some advice for the future as well. Oh, sorry, I moved my camera. It's just that it takes a lot more internal structure and organization than you might think, because all of us are students, and some jobs in the industry as well. Just from the nature of our university, is very close to industrial partners, and as such, it can be tough to, it can be really easy to underestimate how much organizational load is in here. I think we've seen the timelines, and there's the cooperation with the program so far has been great, but also the reviews are very tough on us. Like the standards are high, and they should be high because we're working on rockets here, and as such, there's a lot of things that need to be done. And getting all those things done, even if you have a lot of people, takes a lot of organization. I think that's been something that's been underestimated so far. Like it's easy to underestimate, and I see it at least in my team, especially, where there's a lot of things that are really tough to manage. Like especially, for example, on the software side, where there's so many things that are constantly changing because of the shortages. For example, in the chips, we've had several instances of like challenges so far where we wanted to use a certain sensor and then we tried to order it, and then the producers were saying that they don't have it anymore. They never produce it because of the chip shortage, and that's been tough. So we've had to constantly restructure and reflow. And I think to give advice to future testers and participants is to go along and try to foresee where things might go wrong, have a backup, and test as much as you can. And like, don't underestimate the organizational load. I know we were students here, we just want to try and work on rockets, but it really does make things easier if everyone has a task that they're working on. That was, I think, how I would sum this up.
Great.
Yeah,
So, yes, of course.
Well, I was just going to add that from my side, I have a more technical thing I want to give to other students for the future. I mean, I do agree with Timo. It's a lot of organization, and it can be quite tough sometimes with the reviews and to get everything done in time. But we succeed. But from the technical side of view, I would give the advice to always rethink your design, not too much, because if you want to constantly optimize, you'll never finish. So you have to find a fine line there. But I will say that we, for example, for a long time, we wanted to only use one parachute, and that made our experiment very complicated. And after seeing the review and the help from the REX organizers, we were rethinking that system, because it didn't make much sense to make everything in the experiment so much more complicated, but to then have a more easier parachute. And so we had to rethink the whole system, changed quite a lot, actually the whole experiment, at least the inside of the experiment, obviously not the transpiration cooling. And we changed all that, even though we didn't want to in the first place, but it was one of the better decisions, or even one of the best decisions we did to actually realize this experiment, because this would have gotten a lot harder than before. So yeah, that's my advice to future student teams. It's better to change something for the easier than to stick with the old ways. But also don't optimize too much or you'll never finish. That will be my closing sentence.
I think we've
This
seen
goes
quite a bit of
especially
that
for the
ourselves.
Oh, sorry. Go ahead.
No, I was gonna say that we have similar views due to our experience in the REXUS BEXUS. So you need to stop optimizing at some point. It's very relatable.
Yeah, sometime you just have to say that this is a go. Like,
It's good enough.
it's good enough. So I think this would wrap it up for the first interview of our new live series, Discussions in Orbit REXUS BEXUS Edition. We want to thank everyone that tuned in to watch the interview, and of course a special thank you to Trace, the first team to be interviewed with us. Thank you very much, Team Trace, and we hope that everything works well in your experiment, and we wish you the best.
Yeah, we hope to see you there.
Having us.
See you then.
All the best to you also to your experiment.
Thank you very much.
See you on the rocket.
Or in the rocket.